full professor in computer science and artificial intelligence at the Universidad Politécnica de Madrid. His research interests are primarily in the areas of probabilistic graphic models, meta-heuristics for optimization, data science, classification models, and real applications of biomedicine, bioinformatics, neuroscience, Industry 4.0, and sports. He has published more than 150 papers and impact factor journals and has supervised 20 PhD theses. He's a fellow of the European Association of Artificial Intelligence Science 2012 and that of the Academy of European Science 2018. He has been awarded the 2013 Spanish National Prize in Computer Science and the prize of the Spanish Association for Artificial Intelligence in 2018. In 2020, he has received the Amit Research Award in Machine Learning in New Delhi. The Dr. Concha Bielza is a full professor of Statistics and Operation Research with the Departamento de Inteligencia Artificial de la Universidad Politécnica de Madrid. His research interests are primarily in the areas of probabilistic graphic models, decision analysis, meta-heuristic for optimization, data mining, classification model, and real applications such as biomedicine, bioinformatics, neuroscience, industry, and sport analytics. She has published more than 120 papers in impact factor journals and has supervised 17 PhD theses. She was awarded the 2014 UPM Research Prize and in 2020 by the Amity Research Award in Machine Learning in New Delhi. Finally, Dr. Bojan Mihaljevic is a postdoctoral researcher in the Departamento de Inteligencia Artificial de la Universidad Politécnica de Madrid. His main research interests are the areas of probabilistic graphic models, machine learning, and application in neuroscience. He has published 6 papers in impact factor journals and is the author of the Bayesian Network classified R packet. After the before starting the tutorial, I am going to give you some instructions about the dynamic of tutorial. Please keep the microphone and camera off during the presentations. The question will be answered at the end of each tutorial session. In the chat session, enter your question, which will be answered later. Any another question, please direct it by means of private message to me, Arroyo Figueroa. Okay, welcome, Pedro.
Okay, thank you very much, Gustavo, for this kind presentation and for giving us the opportunity to share with you these 4 hours speaking about Bayesian classifiers. So this is my second tutorial in MICAI. The first one was long time ago in 2002 in Mérida in Yucatan, and I had very good memories for that conference. At that time, the title of the tutorial was Estimation of Distribution Algorithms, and I was the only speaker. Today, we are 3 speakers from the Computational Intelligence Group at the Universidad Politécnica de Madrid. And I would like to say some words about the group. As you mentioned before, our main interest is in the area of machine learning and especially Bayesian networks. We are also interested in feature subset selection, clustering, supervised classification, multidimensional classification, multi-output regression, and in the last 3 or 4 years also in data streams. From the practical point of view, we developed some application in neuroscience, in health, in industry, as well as in sport. And during this tutorial, we will present different methods and approaches for unidimensional Bayesian classifiers and multidimensional Bayesian classifiers. We will also introduce some R packages, 2 R packages, the BN-Learn and BN-Classify. This second one has been developed in our research group, especially by Bojan Mihaljevic. We decided to record our session trying to avoid connection problems. And as you mentioned before, each session length is about 1 hour. After the session, you will have the possibility to ask for questions, remarks, and so on. Unfortunately, I have a master class here in Spain at 10 o'clock in Mexico time. So my colleague, Professor Concha Bielza, will respond the question related with the first session. So Gustavo, we can start with the first video when you want.
Okay.
So good morning to everybody. We will start with the first part of this tutorial.
I can't see the video.
Bayesian classifiers. This first part will develop different algorithms, different approaches for unidimensional Bayesian classifiers. So it means that we are interested in predicting only one class variable, and this prediction will be done in a probabilistic manner. So we will obtain a posterior probability of the class variable given the instance to be classified. Probably you are aware that there are several different ways for doing supervised classification. In some cases, we don't have a probabilistic output. We will call this non-probabilistic classifier. And examples of this non-probabilistic classifier include rule induction, classification trees, super vector machines, artificial neural network, and so on. However, there is other paradigms as Bayesian classifier where the output is probabilistic. And these include logistic regression, discriminant analysis, and of course, Bayesian classifiers. We will concentrate in this talk on discrete Bayesian classifier. It means that our predictor variables will be categorical. They are not continuous. Or in other words, if they are continuous, we decide to discretize these continuous predictors. This is the outline of this first part of the tutorial. We will see 4 main topics: augmented type base, Markov blanket-based Bayesian classifier, unrestricted Bayesian classifier, and Bayesian multidens. So as you probably know, one of the main topics in machine learning is supervised classification. We will see several samples as this optical character recognition, where we can have several instances. Here we have our third instance. The label corresponding to this instance is 9. We will obtain features, the predictor variables, from the image of this optical, of this character, of this 9 character. So we will take into account the pixels of this digital representation, and these are our predictor variables. We can do the same with the rest of the samples. After working with all this data, we will obtain a model able to classify new or to recognize new optical characters. Another sample is this very popular issue in bioinformatics, the prediction of the secondary structure of proteins. According to biology, the function of the proteins depends on the secondary structure, and this secondary structure refers to the folds, the different ways, the different possibilities to fold for each of the amino acids. So the idea is to open a window centered in the amino acid where we try to predict the type of fold, and then using some labeled samples to develop a new classifier for this issue. This sample is completely different weather forecast. Here we are interested in, for example, predicting the temperature in Mexico City for today and for tomorrow and for next week and so on. Perhaps we are interested in predicting this every hour. And our prediction can benefit from the prediction in Guadalajara several hours before. And our prediction is perhaps not only in the temperature, we can be interested also in, for example, the windy or humidity or snow or any other characteristic, in this case, more than one class variable. As we will see, this is a topic of our second session of the tutorial. But what is interesting in this example is to remark the spatial and temporal characteristic of the problem that is different from the previous one and constitute a more challenging problem than the two previous. From one abstract point of view, we have something like this. We have capital N instances. Each of them is characterized by small n predictor variables. And in addition to this, we also have the label of each instance, depending on the problem. Using all this information, using this information in this table, we would like to induce a model, a supervised classification model in an automatic way by applying some algorithms, and then our model will be used for the prediction of other instances where the class variable is unknown. This is more or less the use of supervised classification in this unidimensional learning problem. When the supervised model is obtained, what we are doing is see in the figure where three dissonant decision regions in red, green, and blue are obtained. As you can see here, we have decision boundaries. This is our first decision boundary, our second decision boundary. And the decision boundaries separate the decision region. And as you can imagine, the more flexible the decision boundaries, the better performance of the classifier will have. Interesting in obtain an analytical expression of boundary for each of the different paradigms. In our case, we obtain for discrete Bayesian network classifier for almost all the elements of this family of classifier, and it was published in the Journal of Machine Learning Research. So let's remember some issues about performance estimation, performance measure of classifiers. And to introduce, let's consider the most simple problem that refers to a binary classification where the variable can only get possible values, let's say negative. And of course, our model, our supervised classification model, also predicts positive and negative. Here we have four possibilities. We have a possibility where the true class is positive and the model is predicting positive. This the number of cases where this happens are called the true positive examples. We also have the false negative examples where the true class is positive, but the classifier say negative. These are mistakes. We also have mistakes, the false positive example. The class is negative, the classifier is positive. And finally, we have true negative examples where both the class and the classifier set negative. So according to this confusion matrix, we can define several performance measures as we have here in the slide. For example, we can define the accuracy of the classifier as the percentage of correctly classified samples, or we can define the sensitivity or recall that refers to the from the positive samples, how many of them or which percentage are correctly classified by the model. Or we can speak about the specificity, the same concept with true negative, or the positive predicted value, negative predicted value, or some elements of the F measure, as here the F1 measure that refers to the harmonic mean between the precision and the recall, or other more statistic coefficient as this Cohen-Kappa statistic computing as an independence measure between the behavior of the classifier and the true class. So all these quantities, all these measures fall
within the interval 0, 1, and the values that are close to 1 are preferred. One important issue here is how to estimate these measures, and not only these measures, because there is a plethora of different measures to study the performance of a classifier. For example, we can be interested in the area under the error curve, or we can be interested in the prior score, or any other performance measure. But what is interesting is to consider that all these estimations should be done in an honest way. Here we represent the different possibilities for doing this estimation honestly with single resampling or with multiple resampling. I will concentrate on these two methods, holdout and K4 cross-validation, as example of single resampling. Notice that in multiple resampling, the main idea is to repeat this single resampling several times and compute the average and the variance of the different estimations. So in holdout, the main idea is to split our original data set D into two subsets, two disjoint subsets, the training data set and the testing data set. So by doing this, we will learn our classifier by using the samples in the training. This is our classifier. We will test the classifier. We will estimate the performance measure of this classifier over the testing data set. So this is honest in the sense that this estimation of the accuracy of the classifier is done over the testing data set, and these samples are not in the training data set. So, okay, this is a way to do the estimation honestly, but our main problem with this approach is that the final model, the phi, is a model that is obtained with a subset of the original data set. So it's not efficient in this sense because we are losing information of the testing samples in order to induce our model. Trying to avoid this problem, there is another method that is more popular nowadays. It's called the K4 cross-validation. Here the idea is to split our original data set into K false in such a way that the intersection between any pair of false is the empty set, and the union of these false is the original data set. The model is obtained with the whole data set, with the capital N samples. And all this part here is done in order to estimate the accuracy or any other performance measure for the final model phi. And the way to estimate this, according to the K4 cross-validation, is as follows. I will consider the first fall, and this first fall is here waiting to be tested. And this is the testing subset for this classifier. This classifier has been obtained with the rest of the false. We do something similar with the second fall. who is here waiting to be tested with this classifier. This classifier is obtained with the other 3 false, and so on for the rest of the false. After computing these 4 accuracies and with the average of these 4 accuracies, we will obtain one estimate for the accuracy of our model phi. There are 2 examples that are quite popular in this K4 cross-validation. One is called leave one out cross-validation. People use this with a small data set because in this case the number of false is the same as the sample size. So it means that you will have here only one example to be tested. The same in the second test and for the rest. And the other interesting K4 cross-validation example is the stratified K4 cross-validation. Especially interested with unbalanced data set. The main idea is to maintain in each of the 4 the same percentage of positive examples as in the whole data set. Okay, we need another element before to introducing the different Bayesian classifiers, and the other element that we need is Bayesian networks. I will introduce this concept with one hypothetical example that we call risk of dementia. Here in this graph, we are representing the relationship, causal relationship between 5 variables: age, neural atrophy, stroke, dementia, and paralysis. And as you can see, we are assuming that neural atrophy and stroke depends on age. These two variables, neural atrophy and stroke, are parents of dementia. Dementia depends on these both variables, and also paralysis depends on stroke. And the way of representing these dependencies is with these CPTs, conditional probability tables. For the case of age, that is a root node, we only need to specify the marginal distribution. Notice that we assume that all variables are binary. For the case of dementia, we need to specify the posterior or conditional probability of dementia given any combination of his parents, neural atrophy and stroke. And for the case of paralysis, we need to specify the conditional probability of paralysis given stroke. So using this qualitative part that is represented by this directed acyclic graph and this quantitative part, conditional probability tables, we are able to factorize the joint probability distribution of these 5 variables that in general needs this number of parameters 2 to the power of 5 minus 1, because one of them is not a free parameter. In terms of this factorization, this factorization follows the representation in the directed acyclic graph. So we have the probability of H times the probability of n given H times the probability of S given A times the probability of D given N and S times the probability of P given S. In Bayesian network, we say that N and S are parents of D. At the same time, S is a parent of P, A is parent of N and S, and N is parent of D. Okay, so now we can speak about discrete Bayesian network classifiers. We will follow this categorization that we introduced in a review in the ACM computing survey 6 years ago. So the idea is that we are interested in computing the class value C star with the maximum a posteriori probability for each instance X. We will follow a generative approach to this problem, in the sense that when computing this posterior probability, we will consider that this posterior probability is proportional to the joint probability between x1, x2, xn, and c. And this is the n plus 1 dimensional probability distribution that we factorize here. In a general sense, we factorize as the probability of C given his parents in the Bayesian classifier or the Bayesian networks times the probability of Xi given his parents. And this is extended for each of the predictor variables. So depending on how this factorization is done, we will refers to augmented naive Bayes. In this augmented naive Bayes, as you can see, the class variable has not parent. Or we will refer to Markov-Blanket or unrestricted Bayesian classifier. Here we incorporate a set of parents for the class variable. Or we will speak about Bayesian multinet. We are not considering any parents for the class variable, but for each of the predictor variable, the parents depends on the value of C. So we will develop these three different factorization of the joint probability distribution. But before to speak about the different structure, we need to clarify the situation that all these probability here, all these probabilities, or in general in this formula, all the probabilities should be estimated from the data set. And this estimation can be done in two different ways. One is the standard and very popular maximum likelihood estimation, where the probability is estimated for this categorical variable as a relative frequency. Or another possibility is the use of Bayesian estimation. When using Bayesian estimation, we assume a prior distribution over the parameters, and this prior distribution should be conjugate with respect to the distribution of the data. Remember that we are working with discrete Bayesian classifiers, so the predictor variable are categorical, and the conjugate distribution with respect to the categorical is the Dirichlet distribution, in the sense that if we assume a prior distribution following a Dirichlet and the data are categorical, then the posterior distribution is dirichlet again with different hyperparameters. And in this case, using the Liston rule, the estimation of the probabilities is given by this formula that is very close related with the maximum likelihood estimation. Notice that now in Liston rules, we introduce the hyperparameters in order to estimate the probabilities. So let's start with augmented naive Bayes, and in this case, the most popular, the most simple model is called naive Bayes. It was introduced by Minsky in 1961, and the main characteristic of the model is that it assumes that all predictor variables are conditionally dependent given the class. So this provides a factorization in this way. From a graphical point of view, the structure is like this. So we have one arc from C to each of the predictor variables, but there is no connection between the predictor variables. They are considered as conditionally independent. This is very far away from a normal situation in a real world problem. And apart from this, Minsky was able to prove that the decision boundaries for the naive Bayes classifier were hyperplans. And it means that naive Bayes is able to discriminate correctly only examples, only problems that are linearly separable. So this was the main reason for the very scarce use of naive Bayes until the 90s, 95, 96 was the next extension for this naive Bayes model. There is a lot of variants of naive Bayes. Perhaps the simplest one is something called the selective naive Bayes. So the idea, as you can see here in the figure, is to determine which variable are not interesting for the class and reduce the number of predictor variables. And the way to remove these variables is by using, for example, a filter approach to this process that is called feature subset selection. So in this process, we are interested in removing those variables that are not relevant and that are redundant for the class variable. This relevancy is detected using, for example, this concept of mutual information between the class variable and any of the predictor variables here represented by X. So the mutual information between two variables or between the class and X measures the reduction in the uncertainty of C, uncertainty that is expressed here by the entropy of C once the value of X, of the predictor variable X, is known. So this reduction on uncertainty is computed by introducing the concept of entropy of the class variable and the conditional entropy of C given X, And after algebraic manipulation of this formula, we finally obtain this expression where you can see several things. You can see that this expression is completely symmetric. So it means that the reduction in uncertainty in C, when you know the value of X, is the same as the reduction in uncertainty in X when you know the value of C. And on the other hand, you can also see that when C and X are independent, in this case, this numerator factorize as this product, probability of C times probability of xi. So it means that the numerator and the denominator cancel. So this log is equal to 1. This quotient is equal to 1, the log is equal to 0, and the mutual information is equal to 0, something that we should expect, because when two variables are independent, to know the value of one of the variables is not able to reduce the uncertainty in the second one. So people use this univariate filtering or use other approaches, wrapper approaches, where you need to induce the classifier in order to select which variables are the important ones, the variables that are able to discriminate the value of C. And in this case, any kind of heuristic has been used to select the prominent features. Another possibility is the use of a semi-naive Bayes. And this approach relaxes the conditional independencies in the original naive Bayes model, introducing a Cartesian product of the original features, or something that is called supernodes. As for example, in this graph, we can see that we have 5 predictor variables from x1 to x5. And from these 5 predictor variables, the algorithm is able to delete the second one, the fourth one, and in addition, it is also able to merge S1 and X3 in a supernode. This supernode contains the Cartesian product of X1 and X3. It means that if the cardinality of X1, let's say, is 3, and the cardinality of X3 is 4, in this case, the cardinality of this supernode is 12, is the product of these cardinalities. Because here we are considering all possible combination between the values of x1 and x3. Of course, when we try to compute the posterior probability of the class given x, we obtain that this is proportional to the probability of C times the probability of x1, x3 given C times the probability of x5 given C. x2 and x4 are not included in this factorization. So the question is how semi-naive Bayes is able to know that x2 and x4 are not in the final model. I will introduce here one approach proposed by Bassani to this problem. Is called the forward sequential selection and joining approach. This approach starts from an empty structure. The accuracy of this model is obtained by using the simple decision rule, where the most likely label is assigned to all instances. And in a second step that will be iterated, the algorithm considers the best option between adding a variable that is not used by the current classifier as conditionally independent of the features, original or Cartesian product used in the classifier, or alternatively joining a variable not used by the current classifier with feature, original or Cartesian product present in the classifier. Let's see one example. We start with the model that does not contain any predictor variable, and we will compare his accuracy with these four possibilities. The four possibilities that we have, for example, this one, where our model is a naive Bayes with only x1 as predictor variable, or is another one, x2 the only predictor variable, or perhaps x3 as the only predictor variable, or x4 as the only predictor variable. After computing the accuracy, our best model is this one. So in the next step, we now have the possibility of checking the best option between adding or joining. So we will consider x1 as conditionally independent of x2. Remember that x2 is in the current model, so x1 can be introduced in the model as conditionally independent of x2. The same for x3 or the same for x4, or alternatively x1 can be introduced in the model as a Cartesian product with x2, Cartesian product between x2 and x3, Cartesian product between x2 and x4. It seems that this is the best model in terms of the accuracy. And if this is our final model, it means that we have tried with x1, we have tried to introduce x1 in the model without improving the accuracy of this model. So we try to introduce x1 as, this is our first possibility, as conditionally independent of the rest of variables. The second possibility is to introduce x1 as a supernode here with x2 and x4. And this is our second possibility. And the last one is to introduce S1 as a super parent with X3. So another very popular possibility is to avoid the conditional independency of the naive Bayes classifier using tree-augmented naive Bayes. This was introduced by Friedman, and the main idea here is to allow a tree structure representing the conditional independencies between the predictor variables. I will show you one example of the use of the standard method. However, this standard tree-augmented naive Bayes can be extended with the introduction of selective tree-augmented naive Bayes, where several x1 and x5, several initial predictor variables are not in the final model. So notice that the computation of this probability of C given X will be proportional to the joint probability of these 6 variables. And here this joint probability factorized as BC times Bx1, x1 given C and x2. Probability of x2 given C and x3, probability of x3 given C, and so on. So we are considering the structure of this graph in order to obtain the factorization. Here we have the pseudocode of the learning algorithm. What is interesting is to notice that we need to compute this conditional mutual information between each pair of predictor variable given the class. And in addition to this, we need to obtain the maximum weighted spanning tree following the Kruskal algorithm. I will show you one example with these 5 predictor variables. So we start computing the conditional mutual information between each pair of predictor variables given the class as we have here, and then we order these pairs of variables. So the pair x1, x3 is the one with the highest conditional mutual information. And this pair will be, as a consequence of this result, we introduce this h between x1 and x3. Then in the second step, we introduce the h between x2 and x4. We introduce the h between x1 and x2. We try to introduce the h between x3 and x4, but we have problems here. This is not an indirect tree, so we avoid this h, and we consider the next one between x1 and x4 the same problems, because 2 h's arrive to x4. And finally, we introduce the h between x3 and x5. When we have 4 h's, n-1 h's, we have our maximum weighted spanning tree, where the weight of each h is obtained with the conditional mutual information given the class. Now, in this step, we need to consider one of the nodes as a root node, and this is this selection as the root node, and according to this selection, the previous edges are transformed into arcs. So this is the tree representing the conditional independencies between the predictor variables given the class. So in the tree augmented naive-Bayes model, now we impose a naive-Bayes model structure to this tree, finally obtaining this Dan structure. There is another family of augmented naive-Bayes called superparent one dependence estimator. This SPODE approach is an element of something called one dependence estimator, where in this SPODE, each predictor variable is allowed to depend on at most one other predictor in addition to the class. So it means that a TAN structure or a TAN model is one example of one dependence estimator, as well as the SPODE. In the SPODE, all the predictors depend on the same predictor. This predictor is called the superparent. And all predictor depends on this superparent in addition to the class. In the sample here, our superparent is X3. The rest of the predictor depends on X3 apart from the class C. The important thing here is that we don't need to apply any algorithm for obtaining the structure of a SPODE classifier. The only thing that we need to do is to determine who is the superparent. And trying to avoid this specification of the superparent, there is one meta classifier called average one dependence estimator that averages the prediction of all possible SPODEs. To tell you the truth, these SPODEs should be qualified SPODEs. What is a qualified SPODE? It means that given a sample to be classified X with this representation, these values in each of the variables, and with this value for the superparent, the qualified SPODE needs to verify these constraints. The constraints is that the number of samples with this value in the data set should be bigger than 30. And then for these qualified SPODEs, this average one dependence estimator will compute the average of the predictions, average extended to this subset of SPODEs, that is the subset of qualified SPODEs. By working in this way, we avoid model selection, and we only consider qualified SPODEs. Another possibility to extend the tree augmented naive Bayes classifier is the use of the K-dependency Bayesian classifiers introduced by Saham in 1996. In this case, each predictor variable can have a maximum of K parents apart from the class variable. Here we are representing one example of a free dependence Bayesian classifier. You can see that X4 has 3 parents, X3, X2, and X1, as well as X5, who also has 3 parents, X4, X3, and X1. So we extend the restriction of the tree augmented naive Bayes, and now we allow K parents apart from the class variable. The learning algorithm will consider in a first step, will determine what is the inclusion order for the predictor variables. This inclusion order is obtained with the mutual information between each predictor variable and the class. And in a second step, the parents will be selected, and to make this selection, the conditional mutual information between each pair of predictor variables and the class is considered. Let's see this example where k is equal to 2. And let's consider this order among the among the mutual information, and this order between each pair of conditional mutual information. So it means that we will start introducing X3 in our model, and C is his parent. We will introduce in a second step X1. C will be his parents as well as X3. In the next step, we will introduce X4, and his parents are X3 and X1. And only when we introduce the fourth variable, X5, now we need to select two parents between the possible free variables that are already in the model, X3, X1, and X4. And this selection is done by checking this order of conditional mutual information. So our first candidate is X2, but X2 is not in the list of variables in the current model. So we find X5 for the first time here with X4. It means that X4 is a parent of X5. We continue with X1. So X1 is also parent of X5. And we do something similar when introducing X2 in the model. The last possibility on augmented naive Bayes is called EAN, Bayesian Network Augmented Naive Bayes. And in this type of models, there is no restriction about the number of predictor variables one predictor variables can have. We will define these predictor variables in a three-step algorithm. In the first step, we will select the predictor variables, and this selection is done using again the mutual information between each predictor variable and the class. And now on selecting the best k predictor variables in terms of the mutual information in such a way that the addition of this mutual information is bigger than this quantity that is a number, a threshold between 0 and 1, this number that multiplies the mutual information of all the predictor variables. So here we select the k features that will play the role of predictor variables. And with these k features, we compute the mutual information, conditional mutual information for each pair of variables. And now we will select some edges that correspond to the pairs of variables with the highest values for this conditional mutual information. And this selection will continue until a percentage given by this number between 0 and 1 of the overall conditional mutual information is surpassed. So when we have this undirected model, we define the H directionality, so we transform our edges into arcs by using this rule, where the higher ranked variables point toward lower ranked variables. Okay, in the second family of discrete Bayesian classifiers, we have the Markov-Blanket based Bayesian classifiers. In this case, we are using the concept of Markov-Blanket in a Bayesian network. The Markov-Blanket of a variable, here we are interested in the Markov-Blanket of the class variable, is obtained by his parents, his children, and the parent of the children. His parents, x2, his children, x1 and x4, and the parent of the children, x3. So it means that x5 is not considered in the Markov blanket of the class variable, so it's not part of the final model that we have here. The final model compute the posterior probability of the class given x1, x2, x3, x4, and x5 as proportional to this factorization that follows the structure of the network again. So how to build this Markov blanket? There is a lot of proposal here. I will introduce the original one by Kohler and Sahami in 1996. So it will start with from the set of all predictor variables, and at each step this approach eliminates a variable until we have approximated the Markov blanket. How this variable to be eliminated is selected. The idea is to try to keep this conditional probability distribution of C given the current Markov blanket at time t as close as possible as the probability of C given the whole predictor variables. And we are measuring this closeness by the Kuhlmann-Leiber divergence between the BC given X as the true distribution or reference distribution and B of C given the current Markov blanket as the arbitrary distribution in the Kuhlmann-Leiber divergence. Unrestricted Bayesian classifier is another possibility. Also in this case, we allow to see to have some parents, as you can see in this example. And in this case, the idea is to use any existing Bayesian network structure learning algorithm to obtain the model, our model. And as previously, once this structure is obtained, we will only consider the Markov blanket of the class variable as before. Okay, we have another possibility to obtain classifiers, that is the use of this concept of context-specific conditional independency or asymmetric conditional independency that was introduced with Bayesian multinets. So it means that in this kind of models, we need a distinguished variable. For our example of Bayesian classifier, the distinguished variable is the class variable. As you can see in this example, where according to this structure, when C is equal to 0, we have some conditional independencies between the predictor variables that can be different. This is the idea of context-specific conditional independency, can be different from the relationship among the predictor variables when C is equal to 1. By doing this, we can express some more flexibility in the relationship of these predictor variables. In this slide, we have two examples of multinets. So, as a summary of this first part of the tutorial, I would like to emphasize several things. One, Bayesian classifiers provides a posterior probability for each possible value of the class. So the output of this type of probabilistic classifier is richer than non-probabilistic classifier. These type of models are competitive in terms of accuracy or Breyer score or the area under the ROM curve with a state-of-the-art in supervised classification. And what is perhaps more important nowadays, where people is speaking about transparency, interpretability, explainability of intelligent system, with this Bayesian classifier, we can explain, we can interpret because they are transparent, and of course we can obtain given domain. Just to finish, I would like to comment that we have been presenting different methods for discrete Bayesian classifiers. Predictor variables were discrete. Of course, we can extend or adapt this method for continuous predictor variables, sometimes assuming Gaussianity, sometimes assuming non-parametric distribution as kernel distributions. And we can also adapt in a quite easy way this classifier for temporal scenarios with dynamic Bayesian network classifier, or for example, with continuous time Bayesian classifier. So here you have a list of the references that we have seen during the slides. And that's all. Thank you very much for your attention.
Thank you very much, Pedro. We start with the question session. And we had one question. From Enrique Zucker. Can you comment of the computational complexity of the different types of Bayesian network classifiers?
Well, Pedro is not here, as he told you.
Yes.
Hi, Enrique. Nice to meet you again. Well, I think that there is a paper, I don't remember now, maybe from people in Granada, here in Spain, or in Almeria. They comment on, I think that I am remembering like a table with the computational complexity of each Bayesian classifier in terms of space and time, both. So here we haven't dealt with this. Perhaps those interested in this issue can consult this reference. I'm not here now. I'm not sure now what is this reference. But well, for instance, it depends on the algorithm. But if you are like I mean, if you are with a TAN structure, since the only thing that you have to compute is the conditional mutual information of the pairs of variables given the class, then the complexity is well, the number of mutual informations that you have to compute, and this has to do with the number of pairs that you can try, and this is at most n, where n is the number of variables, n over 2, and so on. So this is not very complex. Of course, when you increase the complexity of the architecture of the classifier, then it turns more difficult. For instance, I don't know, for the Markov blanket, perhaps this is harder, but this is just because of that reason, because you need to perform many conditional independence tests, and this perhaps you don't have enough data for testing in a reliable manner, because you have to condition on big so on many and many number of more and more number of variables. So if you condition on many variables, then you have to fix those instances fulfilling with these values, and perhaps you at the end you don't have enough data, and the tests are not going to be reliable. So this is what I can comment on.
Okay, thank you, Concha. Let me check about the social network. When we had a question, could you describe some application of Bayesian classifiers in medicine or industry?
Or industry. Well, in industry, the typical problem is when you have a machine and you would like to detect whether the machine is working properly or not. So you can have this kind of labels, or you can have multiple faults. That this will be what we will see in the next video, in the next session, in the next hour, because this is a much more difficult problem. You can distinguish between different faults in the machine. So this is what is called a multi-dimensional classification problem, where you have many class variables, not only one. So because many faults can occur simultaneously. So this is a different thing, and perhaps the faults are related among them. So we will see in the next session, in the next hour of the tutorial, this kind of issues. And also in industry is very important, the dynamic component. So the machine is always working and doing things, and perhaps your classifier that you have suddenly starts to say, okay, this is not fitting this model is not fitting the data. So you mainly have to detect like an alarm that your model is not being valid anymore, and then you have to relearn from the new data set that is arriving a new model. So this process of relearning with the new data that arrive, for instance, in a data stream, by detecting whether there is a concept drift, is an important issue. And in medicine, there are, well, lots of examples. For instance, whether you suffer from a disease or not, yes or no, or what is the probability of dying from coronavirus, for instance. We are now involved in a problem related to COVID-19, and then we would like to, with the data set from several hospitals and people that have been admitted in the hospitals here in Madrid, we would like to classify them according to whether they will be intubated or not, whether they will be they will die or not, or whether the treatment is going to be efficient or not. This kind of issues. Well, there are lots of problems in neuroscience. Also in neuroscience, we have been working with neuroanatomy, and we can classify neurons, for instance, according to different types, because neuroscientists used to name the neurons according to different names. So we have like a list of let's say 10 names, and then we have the neuron characterized by some morphological variables, like I don't know, the length of the first segment of its shape, and then the angle for the bifurcation and so on. And then with all these variables, then you would like to classify this morphological shape, which is a neuron in this case, into these 8 names. So this is another problem where we have been working on.
Okay, thank you, Concha. Other question is when to use each of these models depends on the characteristics of the mind.
Yeah, this is also an issue always when you are learning a model. I mean, this is the same as wondering about whether to use a logistic regression or a support vector machine, or why using a Bayesian classifier. Well, Pedro has told us that, as you have heard, that Bayesian classifiers are transparent, so you can see what are the relationships between the variables. So this is a good thing that we can seek. But if we decide to use Bayesian classifiers, which of them to use? This is the question, I think. So perhaps, well, in fact, there is a theorem in machine learning that states that for any, this is called the non-free lunch theorem, and it states that you are not going to have or to find the best algorithm for that behaves well for any data set. So at the end, this means that you have to try with many models, with many classifiers in this case. So you will typically start with a naive Bayes because it's very, very simple, and sometimes it is enough. So, and there is a principle in science that is called the parsimony principle, or the Occam razor, that states that, okay, if this is simpler, it is better. So why not starting by the naive Bayes? So, but if this is not good enough, or because perhaps you suspect that there is that the conditional independence of the variables are not held given the class, then you will go to another more advanced architecture like the TAN or the VAN or Markov blanket and so on. So you will typically try with many, but starting from the simplest.
Okay, thank you. No more question for the moment. We start with the second part of the tutorial. Thank you.
Okay, you can play my video.
Let
first introduce myself. I am Concha Bielza from the Technical University of Madrid. I co-lead the computational intelligence group with Pedro Larrañaga that gave to do the talk before. So this is the second hour. In the first hour, you have seen Bayesian network classifiers, but from the point of view of having only one class variable. In this case, we are going to move to multi-dimensional Bayesian network classifiers. So this is the outline. So we'll first start by distinguishing between the multi-label classification and the multi-dimensional classification, which is a very easy issue. Then I will give you some very simple methods that are three: binary relevance, classifier chains, and label power set method. Then I will focus on multidimensional Bayesian network classifiers, which is our main topic here. I will give some definitions on MPCs, multidimensional Bayesian network classifiers, and some of them that are specifically designed to be more tractable, which are the CV decomposable MPCs. Then I will give some learning methods of both of them, and some other structures or classifiers more advanced. Finally, some other issues. Finally, I will talk about an application that we have been working on related to Parkinson's disease. Finally, the conclusions and references. So let's start with the multi-label classification, which is a very well-known. Well, there is a big deal of literature around this multi-label classification, where you mainly have not a class variable, but many. So you have, and all of them are binary, as you can see here. So you have some instance, and then you would like to classify each instance according to simultaneously many binary class variables. And this is, well, the idea is that all these variables are related, and this is why this has, this makes sense, because otherwise we can perform independently different classification tasks with only one variable, and that would be the solution. But this is not the case. In general, we expect them to be related, these class variables. So, but all of them here are binary. So this is multi-label and single label, multi-label classification. So examples of this, well, we have many. Here we are, we have the simultaneous object recognition in images, where you have this kind of image, and you have to say whether there is a sky or not, or airplane, or grass, or here a building, a tree, a road, and so on. So you have different labels that perhaps they are present or not in the image. Another example is to suffer from different diseases at the same time. So you may have several diseases at the same time, yes or no. And this is the medical diagnosis, typical problem, medical diagnosis. So this is another example of multi-label classification. And in industry, we can also perform diagnosis of different faults in machine. So let's move now on to multi-dimensional classification. In this case, we have also many class variables, but they are not necessarily binary. So we have here like 0, 1, 2, and 3 values, or 4 even, or whatever. So this is, well, because in principle, in many examples, we are going to have more than binary classes. So for instance, we can categorize a call type where the features, the predictor variables may be extracted from acoustic signals, and the class variables, well, here we have 4, the age, which has been distributed into 4 intervals, the gender, the race or ethnicity, and the mood, happy, calm, sad, angry, and so on. So depending on this, all of the voice, the call, you can classify the call according to these 4 classes. This is one example. Another one where we have been working on is related to neuroanatomy, where you have some neurons characterized by some morphological variables related to their shape. And then you would like each of them to be classified according to the species, to the neuron type. In this case, there are some names that neuroscientists use very, very commonly. Brain region where the neuron is, or the age. So we have these 4 class variables that are not necessarily binary, as you can see. In this other problem where we are interested in the prediction of the stock market value of Dow Jones companies. So Dow Jones companies, maybe we have like 4 companies, and we would like to predict this stock market value from the stock market values during the last week. So in this case, the interesting thing is that we have this multidimensional problem, but also we have time. So time is involved in this problem, and it's an important issue and has to be taken into account. And finally, in this case, where we are interested in weather forecast, we have again multidimensional and time, but also space. Because here we have different meteorological stations measuring different variables, like these ones, related to temperature, wind, and so on. And then we'd like to predict temperature, relative humidity, rain, and wind according to different categories. But here, the important thing, or the new thing with respect to the previous examples, is that we have also the space. We have the space where each region is located and has to be taken into account, because perhaps neighbor regions are more similar to distant regions. Okay, so this is the interesting thing, or interesting issue. So let's go to some notation in a multi-label and also in a multi-dimensional data set. Case, we have a data set with capital N training examples. So each of them is, as we saw, a vector of variables for the features that each of them has this kind of sample space, and then the Cartesian product of all of them gives the space, the sampling space of the joint or the vector of feature variables. For the classes, we have the same case. We have again a bold face here because we have a vector of values for each of them. So we are mainly given notation for this kind of tables that we face. So this is our data set. We are going to learn a model from the data set. So the learning task for this multi-label classification paradigm is to find a function phi that starting from a sample, from an example or an instance x1 up to xn in the feature space, is going to project it to the class space, to the joint space of all the classes. So we expect this function to give the vector of the variables of the components C1 up to CD. So this is the multi-label classification paradigm, or the multidimensional paradigm as well. The only difference is the cardinal of each of the classes here, binary or not. You can see some reviews on this topic in these 3 papers that are very illustrative of the multi-label classification problem. In multi-label classification, we can distinguish 2 big categories of learning methods. One are the problem transformation methods, and the other one is the algorithm adaptation methods. So the first one, we mainly transform the problem into one or more single label classification tasks. So this is the important thing. So we transform the problem into single label classification tasks or single class problems. So this is well, there are some tricks, let's say, to do that. Important thing is that they are algorithm independent. So this is like a very general procedure. So some popular techniques here is binary relevance, classifier chains that we will see in a moment, or this is in binary classification. In multi-class classification, we have the label power set, because here we are going to work with many values for the class. Here we only have binary. Finally, if we identify the label dependencies, we can see other methods like correlation-based pruning or LVPR algorithm. So, for the algorithm adaptation methods, this is very different, because we adapt or extend the current learning algorithm to handle multi-label data directly. So we handle the multi-label data directly, and we can use any base classifier to do this. So the literature, we can see examples that use classification trees, neural networks, k-nearest neighbors, support vector machines, random forest, and also Bayesian networks. So as you can see here in blue, we are going to now to focus on how the Bayesian network classifiers can be used in this context of binary relevance, classifier chains, label power set, or as models that are used in algorithm adaptation methods. This is the case for the NBCs or the multidimensional Bayesian network classifiers that we will see. Okay, so there are 2 main, there are many more, but the 2 main performance measures for assess how good is a model, a classification, multi-label classification model, is the mean accuracy and the exact match. The mean accuracy, so you have your real labels and your predicted labels given by your model. You would like to measure how good this model is performing. So in this case, the mean accuracy is just looking at each column, at each label separately, and it's going to measure how good is matching each label separately. So for instance, here in the first column, we are hitting 1, 2, 3, 4, and 5. So all of them are correct. In the third, for instance, the first one is not correct. The second, yes, yes, no, and yes. We have 3 over 5. And so on. So we can look at the hits or the matches per class, and then compute the average, then average over the 5 the number of classes. So this is the mean accuracy. So in this case, we have here that all of them have been correct for the second as well, and for the last one. Here we are just having 3 correct classifications. So at the end we have over 5. This is the mean accuracy. The exact match is much more strict because we are interested in looking at the whole vector. So we count that this is one hit if we have the correct vector in all the coordinates. So this is, and then of course we compute the mean with respect to the number of instances, capital N. So we have to see an exact match in all the components of the vector of the predicted labels with respect to the real labels. So in this case, we only have an exact match in the second and the third. This one is equal to this one, and this is equal to this one. So we have 2 over 5, which is of course much lower than the accuracy because this is more strict. Okay, so these are the main performance measures that we are going to have to assess how good is my model. So let's look at these very simple ideas that we can use for transforming the problem into a single label classification problem. So binary relevance is the simplest approach, where we have this multiple problem, and then we split this problem into 4 problems on the class. So we have classifiers here, and here, and 4 binary classifiers here for each label. So the classes are related, they are captured this relationship. And then, of course, when it arrives, we will the concatenation of the models. And for learning each of them, each classifier, we can use, for instance, Bayesian Network classifiers. And as you can see, you can imagine, we can use any of these methods or architecture or models according to different complexities, from the naive Bayes to the Bayesian multinet that you have seen in the previous hour of the tutorial. We can use any of them for performing this binary relevance. So, but this is very, very simple. The smarter idea is to use a classifier chain. A classifier chain was introduced in multi-label classification by Reed, but hadn't a probabilistic interpretation. Then in this other paper, we have the probabilistic interpretation, where, well, mainly as you can see, this is our aim to compute the posterior probability of the class, the vector of classes given the vector of features, and we can use the chain rule to write this expression as the probability, for instance, of C1 given X, then C2 given C1 and X, and so on. So this is the chain rule in the probability theory. So by taking this idea, we can transform, because we are still with the problem transformation methods, so we are going to transform the multi-label learning problem into a chain of binary problems, binary classification problems, where we are going to use as predictor variables not only X, but the predictions given by the preceding classifiers. So when we are in the moment of predicting CI, this class, we are going to use the feature variables, of course, but also the previous predictions given by the previous classifiers. So this is the same as saying that our phi is going to be built from, it's going to be learned from the features, but also from the predicted labels given by the other classifiers. So at the end, we are going to give as the output of this step of the chain for CI this probability. Well, of course, we could say, okay, but I have this real labels. Why not using them instead of their prediction? Well, it could be done like this, but only in training time. If we are going to use the phi model to predict later on an unseen instance, then it is not. We don't have these labels, so the method necessarily uses the predictions by this reason when we are in classification time. So, but of course, we could mix both. So some of them being used for the training time and the others for the classification time. As you can see here, we are using an order of the classes, and of course the result of the chain depends on it. So with Bayesian network classifiers, we can use this idea, and this is what we did with in this paper with some people from Mexico with the 3 naive Bayesian chain classifiers. So in this case, we are going to build a classifier chain. To decide what are the variables here in the chain that we are going to use for as predictor variables, we build first a time structure for the classes to try to capture the dependency structure among them. So like this, so we learn a time structure with the data coming from the classes, and then we start with the chain classifier. So for instance, in this case, we propose to use a very simple idea, an base as a baseline classifier. So we are going to build, for instance, for C6, an base with the predictor variables, but also with a predictor variable that is its bind. So C3 will be used here for C6 as a predictor variable. So for C5 also we would use C3, for C5, C7, sorry, we would use C6, and so on. So for CI, its bind, because there is only one, because this is a tree, is used as an additional feature. And of course, to classify a new instance, we concatenate the outputs of the chain as any chain as here. So we are going to give here a predicted label for CI, here for C1, and so on. So here is the same. Of course, building a time structure is it's not giving us a unique tree, so we can decide which is the root node of the time by using different heuristics. In this case, in this paper, we propose to use to select this root node at random, or we can take a node with the largest number of incident edges. For instance, here C6 has 3 incident edges. The node with the best classification accuracy would be another criterion. And also we can use an ensemble of all these models to avoid the selection of the root node or the influence of the order, how we concatenate the classes. So in this case, this was what we did by building an ensemble of trinary Bayesian chain classifiers, giving us best results than only using one of them. And this is this paper in 2014. But also in that paper, we could expand these ideas by saying, okay, rather than using a tree, why not using Bayesian network with class variables like this one? So we can learn a Bayesian network for the class variables with any structure, not necessarily a tree. And then for this part where we decide which classes will be the predictor variables apart from the features, from the usual features, we will take only the parent classes of each class. So for C3, we are going to use C1 and C2 as predictor variables. For C1, half any. For C2, half any because we don't have parents. And for C4, we are using C2. So we are going to use then a chain, so an order for the classes, and we are going to solve these problems and then concatenate the output. So the important thing here is that we are using any Bayesian network. Okay, so the third method is among this first block of simple ideas is the label policy. So in this case, we maintain the set of variables, but we look at them as if they were configurations from a problem with only one class variable that is having well, in fact, it's a vector class variable having these different labels. I mean, you can say that the 0, 0, 0, 0 is the first one, 0, 0, 0, 1 is the second one, and so on up to 1, 1, 1, 1, 1. So we can enumerate all these possibilities for the four classes, and each of them is becoming a different class value of the unique class variable that we are going to have this transformation. So of course, the problem here is that if we have many classes, then we are going to have many of them not observed. So many of them are going to be absent in my dataset. So this is a problem, and most implementations essentially ignore these combinations that are present. So this is a problem because we are not going to be able to predict these unseen label sets. So this is an example where different data sets that are well known in the literature. We can have, for instance, here 45 classes, but so this would give rise to many combinations for this unique class variable to the power of 45. Of course, this is an important issue, the size of the data set, because we can't have more than the size of the data set, more than the capital N. It's possible to have different number of combinations for the classes. So we have to compute the power of d. But well, in any case, here the actual label set, the actual number of label sets is much smaller. So this is the usual case is that we are going to have many of them not present. Okay, so now it's the time to move on to multidimensional Bayesian network classifiers, which, as you can imagine, this is not a problem transformation method, but an algorithm adaptation method. These two big groups that we distinguish, this is what we have now. So we are going to directly face the problem of multidimensional classification, but with Bayesian network classifiers. So we will look at some definitions of two kinds of dependencies, how to learn them, and then some other issues. So first, definition. So we have this multiple diagnosis problem where we have diseases, 1, 2, up to 3, and then we like to search for this this special configuration that is giving me the maximum of the probability, the posterior probability of the classes with the features. So given that my patient has this values, then this is the maximum probability. So we have to compute the maximum over all the classes of this probability of the joint distribution of the classes. This is the same as, well, can be written like this: probability of C1 CP times the probability of X1 X7 given C1 CP. So this is called the MPE, the most probable explanation. So this is kind of abductive inference, and here we are looking for this specific combination to solve the problem or suffering from any disease. So this is our. And as you can imagine, to have the complete probabilities here, we need a very big number of parameters, because here we need 2 to the power of d -1, because the last one can be derived because all of them have to sum up to 1. And then here for the conditioning part, we need as many as the number of combinations here, because each of them is a different distribution. So we need 2 to the power of d times. Here we need also all these combinations 2 to the power of m -1, because the last one can be derived. So if we sum both this for the first and this for the second, this is a very huge number of parameters, and take into account that now we are considering predictors and classes binary, but it would be worse if we don't have necessarily binary variables. So multidimensional Bayesian network classifiers, or MPCs for short, are a kind of Bayesian networks that are designed for dealing with multidimensional classification. So mainly partition the set of vertices into VC, the class variables, and EX, the feature variables, G and M, given n variables, the total of n variables. Then this is for the vertices. For the arcs, we have different subgraphs. One is so we have this kind of Bayesian network, and we have the class graph, which is including the classes and their arcs. The bridge graph, which is connecting the classes with the features, only in this direction, from classes to features. And then the features graph, including the features and their relationships. So we have these 3 subgraphs. This will be the notation. So depending on the structure allowed in each of the subgraphs, we can have more complex structures. In this case, we say empty, MPC. It means that we don't have any graph, any arc here for the classes and for the features. tree MVC will be a tree for the classes and a tree for the features. Polytree DAG, polytree for classes, and DAG for the features, and so on. So this is a way of including adding a terminology for the family of MVCs. But there are some MVCs that are especially interesting because of their tractability when computing the NP, most probable explanation. And this, well, because NP is generally a hard problem in general Bayesian networks. So this is why we decided to define specific MVCs that are called class-rich decomposable MVCs. With the aim of having tractable computation of the MVC. So let's look at what is this. Class-rich decomposable MVC is an MVC where we have for the classes and the bridge, these two graphs can be decomposed as the union of maximal connected components. So for instance, here we have this MVC, and as you can see, well, the maximal connected component is a connected subgraph where you can find the path, the directed version of their nodes. Between any pair of vertices, you can find the path. It's undirected version. So we call here that we are only looking at the classes and the bridge. So in the classes and the bridge, we can have this path to say that there is one maximal connected component with C1, C2, and C3, X1, X2, X3, and X4. And here with C4 and C5 because they are connected and X5 and X6. Okay, so we have these two maximal connected components, and also there is another property that should be fulfilled, which is the non-shared children property that is saying the children of the classes in one component and the children of the classes in the other component must be different. So we can't have this kind of arc because in this case these two different the children of C3 and C4 would be shared as X4. So finally, so a class-rich decomposable MVC is something like this, where this is not here, of course. So we can find the maximal connected components, and we can remove the arrows of the features graph because this is they are important. And then we have these two parts for the MVC. So these are special, and we will look at them later on for having specific learning algorithms and properties for the tractability of the computation of them. Sorry. Okay, so why defining this kind of MVCs? Well, because we proved a theorem that states that the maximum, the NP that we would like to solve is proportional to the product. This is the components from 1 to R, the product of other optimization problems that are solved in smaller subspaces. So here the maximum here is computed all the variables, the classes, but here we are computing in a smaller space. This means the projection of the whole vector to the coordinates found in each component. So we basically have the usual factorization given in the Bayesian network, where the classes are conditioned to their parents, which are classes as well. But for the children, we have that we have the picture given their parents X. So I mean the parents of X can be features or classes. So at the end we have, well, let's look at the example. But the idea is that we have to obtain this maximum over 5 variables of the joint distribution given the 6 variables here. And this is proportional, of course, to the factorization given by the arcs as in any Bayesian network. But then we realize, according to this theorem, that this is maximum of computed over this smaller space of C1, C2, and C3, which is the first component of these factors involving C, C1, C2, and C3, X1, X2, and X3 and X4. So this first part, and then a maximum over the other component, C4 and C5, X5 and X6. So this is a way of reducing the computational cost of the network. How to learn these structures? Well, in this paper we propose a very general procedure, filter procedure for learning the general structure of DAG, directed acyclic graph, NPC for the classes and for the teaching. Since this is a filter approach, we use any score principle, a penalized likelihood or Bayesian score, and then we propose to follow a search in 4 steps. Let's look at one example. So we first learn the class of graph with some features score, as in other situation with Bayesian network, for instance, the K2 score. And then once we have this class of graph, using the data related to the classes, then we learn the features of graph here, given a candidate bridge graph. For instance, we can start with an empty bridge graph, but then it's going to be different in the next iterations. So the idea is that we learn these features of graph once we have the bridge graph, because the parts are well conditioned on the classes. This is a way of connecting the class of graph and the features graph with the 2 parts. So we need this bridge graph. So then we move to other candidates bridge graph by using the best first approach, which means that we add 1 arc whenever this is improving the score. And then we learn again the features of graph given this new bridge graph. So we repeat this 2-step procedure of bridge and feature graph, and we stop if we don't have any improvement in the score. This was the idea that we proposed as a filter approach for learning BC. Then in the same paper, we gave a wrapper approach where we mainly look at the accuracy, for instance, the exact match that was more strict. And then whenever we have any arc that can be added to my graph, then I add this arc and assess whether this is improving the accuracy or not. If this is not improved, then I can try with another arc, or this is improved and is updated, and I continue this way whenever we have an improvement in the accuracy. So how to learn these other structures, these simpler structures, simple composable indices? Well, in this other paper, we proposed to follow 3 phases. This is quite different from the previous approach. for general disease. We start here with the bridge of graph. So we start from an empty graphical structure and learn for each class a selected naive. So we take C1 and learn selected naive. And we have some accuracy for this selected naive. Of course, we have also some ranking for the features. Imagine that X5 has entered the model the second and X2 the first, and so on. So we have this kind of information. And then if we join all these structures as a whole, we are going to violate the second property of non-shared children. So to avoid the violation of this non-shared children property, we are going to, because for example here we have X5 and X5. So we have to remove all common children, because otherwise we are not going to have this property. How to do it? Well, we have two criteria. First, we can say, okay, this X5 was the second to enter this model. But however, here it was the first, so I will keep X5 with C4, and then I will remove this variable here. Or, for instance, if I don't know, another variable, this is feature insertion rank. We are mainly taking into account the position or importance of the variable when we're building the selected naive. But if the two variables have the same rank, when building the conditional selected naive, then we can look at the accuracy of each of the models and when entering these variables. So if one is giving a lower accuracy, then it would be. So this is the decision of having finally the non-shared children property L. So at the end, we have something like this, which is only the bridge graph, and we have the C decomposable C with as many components as classes. And now we learn the features of graph. So we fix the maximum number of iterations, because this can be very, very costly, computationally costly. So we decide at most a fixed number of iterations. And then in each iteration, we decide to select at random an arc between a pair of feature variables. And we add it if the accuracy is improved. Otherwise, it is discarded. So here we are adding these two arcs. Then in the last phase, we are going to try with arc additions between the class variables. So here we are adding this arc. So we are adding the arc that improves the accuracy the most. So in this case, from 4 components, maximal connected components, we obtain only 3, because we are joining these 2.
So after that, we try to update the bridge graph inside, but only inside the new induced maximal connected component. So in this case, in this part, in the first connected component, we add this, for instance, this new arc to update the bridge. So this is not very costly, because we are only updating one component. And then again, we update the features of graph by inserting one by one additional arcs between feature variables. In this case, we are inserting this and this. And then we iterate over these 3 steps until we don't have an improvement in the accuracy, or we have just one connected component. So as you can see, we are merging the components, starting from the number of classes to perhaps one or not, we can stop earlier. So, and very recently, we are proposing to build a hybrid between a classification tree and an MVC, and we call it an MVC tree, which is a tree where in the leaves we have MVCs, as you can see here. So the internal nodes are feature variables that are splitting the data and in standard classification trees, and we have some branches that are corresponding to the possible values for the variable here in the node. And in the leaves, the new thing is that we have MVCs at the leaves. So to learn this kind of structure that is giving us specific relationships depending on some attributes for the MVCs, which is smarter, but the learning is very, very complex. In this case, we propose to follow a wrapper approach in a greedy way. So we mainly start deciding whether to split or not the node according to the exact match accuracy. So this is wrapper, starting from one MVC. So if we have one MVC is performing splitting is correct or not, is convenient or not, depending on the accuracy. So this is the way we learn this kind of structures. So some other issues that are interesting to look at. For this, I recommend you to go to this review that we wrote very recently, and it's about MVCs. Mihaljevic and others, Pedro and myself. So in this review, we have this kind of tables where we are saying, okay, beyond this exact match and mean accuracy, we have other performance evaluation measures. Some of them are borrowed from multi-label classification. So this kind of other measures like the area under the rock curve, the Brier score, and so on. And another important issue is the complexity of obtaining the NPE. The NPE, the most probable explanation, is the computation that we need for solving the problem. And in Bayesian network is something, it's a problem which is NP hard. But it can be computed in polynomial time, so this is the same as saying that it is tractable if its tree width is bounded, the tree width of the Bayesian network. So what is the tree width? Well, the tree width is something that has to do with the chordal completion of the graph or the triangulated graph. Has something that belongs to the graph theory. And then, so you triangulate the graph, and then you look at the size of the largest click. Click is a completed subgraph. So, let's say that you are looking at a big group of variables that are related, more or less. So if this tree width is bounded, then you can compute the NPE in polynomial time. What happens for MVCs? For MVCs, there are some results, some theoretical results that, for instance, this first one is saying that the tree width of any graph in MVCs is bounded by the tree width of the features graph plus the number of classes, So this means, by the way, that the class graph is irrelevant. So, and this also means that the NPE can be computed in polynomial time if the tree width of the features graph and D, the number of classes, are bounded. So we have to worry about these two guys to have a polynomial, to have the computation of NP in polynomial time. So this is important. For CV decomposable MVCs, Quizhout went a step further and had this bound for the tree width, which is saying again the tree width of the features graph. And here, this is the number of classes that of the component with the maximum number of classes. So we only need to look at the number of classes of each component, and if it is bounded, and also of course the features graph, then we can compute the NP in polynomial time. In this other paper, we in our group we derived that for DAG NVCs, we only have to bound the number of parents of each feature and the number of classes. So this is easier because we don't have to look at we don't have to compute the tree width, which is not easy at all. For CV decomposable NVCs, the number of parents of each feature again, but rather than D in general NVCs, here what is important is to bound the number of class variables in each component. So this constraint or these upper bounds on the tree width, we can design learning algorithms that guarantee that the NP is going to be computed in polynomial time. So this can be used for designing learning algorithms. And well, this is a good idea, and this is in the literature you can see this kind of things. In fact, here you have in our paper review we have this table where we compile all the methods proposed in the literature to learn NVCs from data, and you can see that there are score-based algorithms or constraint-based. So it means that they use condition independence test. There are some feature subset selection algorithms. Whether the algorithm is having into account the problem of inference complexity. Here, look at this. We are dealing. This is our paper again. We are dealing with multidimensional concept-based data streams. So we have basically a data stream, and we have to watch or to decide whether my model is still valid or there is a concept drift, and we have to detect whether or not there is a concept drift, and then to change the model accordingly. So here we are distinguishing the learning strategy, whether this is a filter, a wrapper, or a hybrid for the score base or constraint, or which kind of structure are we learning, and whether we are this is extractable or not. So you can have a look at this paper. So to finish this second hour, let me show you one application related to Parkinson's disease that we have in this paper. In this case, there is a questionnaire that is called the PDQ 39 item Parkinson's disease questionnaire, which is a specific instrument to measure the quality of life, to measure the degree of disability in Parkinson's disease patients. So it's something like this. It's a questionnaire saying how difficulty doing the leisure activities which you would like to do. Never, occasionally, sometimes, often, always. So the patient has to fill this kind of questionnaire. There are 39 items, and they can be grouped according to 8 dimensions: mobility, activities of daily living, emotional well-being, stigma, social support, cognition, communication, and bodily discomfort. So this is something which is capturing the patient's perception of his illness. Okay. There is another generic instrument. So this is specific for Parkinson's disease, and this is a generic instrument. It's called the EQ5D, European Quality of Life 5 Dimensions. So this is generic, and it measures the health for clinical and economical appraisal. And so in this case, one pharmaceutical company, well, they gave us this problem because this is a way of okay, if I would like to launch my drug into the market, and I have the patient's perception according to this PDQ 39, the government is not going to allow me to launch this drug unless I have these perceptions measured in a generic scale like this. So this is a very generic, not necessarily for Parkinson, and it has these 5 dimensions: mobility, self-care, usual activities, pain, discomfort, and anxiety, depression. From 1 to 3, all of them. So the idea is to map from PDQ 39 to EQ5D. And as you can see, here we have scale of 5 points, and here of 3. So we need a multi-dimensional classification approach. And in this case, in this paper, we propose not a score base, but well, we determine, we basically adapt the Heaton algorithm that is using hypothesis test and conditional independence, like here I mentioned these ones, this group, constraint base. This is not a score-based algorithm, but a constraint base. So here it is the same idea. The Heaton algorithm was proposed for only one class variable, and here what we do is to find as the Heaton algorithm the Markov blanket around each class variable, but then we try to join all this information and giving directionality to the graph over the 3 subgraphs: the class, the bridge, and the feature subgraphs. Well, this is described in this paper. So the results are that we, after using this data set with almost 500 patients, our methods, the CDMBC or the MB-MBC, Markov blanket MBC, we have the best results for the mean accuracy and the exact match, compared with other methods that are, well, this is a multi-nominal logistic regression, that is a binary relevance method because it's using only class by class independently and then concatenating the results. So this is not having into account the relationship between the 5 dimensions. And these 2 are related to regression, because these 5 measures can be transformed with a function into a utility index, and this is what these 2 algorithms are trying to fit this utility index. So, but at the end we obtain the best results, and also we could look at the graphical structure, for instance, of the MB-MBC here. And we could check how the classes here in pink are related, and well, how with the bridge, how classes and features were related as well. And well, we had the experts could interpret these relationships, and they found that it was very, very reasonable. Okay, in this paper of the review, as I told you, we also talk about other applications, mainly in the medical domain. Here you can see this is a paper of our group where we are trying to we are trying to infer HIV inhibitors depending on some mutations which are the predictive variables. Or here these other ones. So these are from our group on neuroanatomy. But there are other applications in sentiment analysis, fish recruitment, and so on. Here you have the dimensions and the model that was used. Okay, finally, the conclusions of this second part is that the MVCs provide a model that extend the well-known multi-label problem. The MVCs are transparent and interpretable models that, by taking advantage of the conditional independencies, require fewer parameters to be obtained or assigned. It considers explicitly the dependencies among class variables. There are some open lines that I would like to mention, like how to extend these MVCs to continuous time, ordinal classification, or how to handle continuous features by discretizing or by using Gaussian variables or even kernel density estimation. Some of these open lines have some contributions already in the literature, by the way. How to incorporate feature weighting or feature subset selection methods, how to deal with the stratified performance evaluation. Stratified performance is to when you are using cross-validation for evaluating the performance of a model in a stratified manner, you are going to maintain the same proportions for the class variable in each fold. How to do it if we have many class variables, as is here in the case of multidimensional classification. So this is a very interesting issue. How to build sensitivity functions for tuning MVCs. What happens with the public domain software? There are only a few individual contributions, and this is very different from multi-label domain, where you can see these four software packages or software platforms to deal with multi-label, but this is missing in multidimensional classification. And this is also the same case for the benchmark repositories. So this is missing, something that is missing, and instead people for testing their algorithms, they sampling from a random MVC or from a given Bayesian network, deciding that these are classes variables, these nodes are class variables, or they use multi-label examples. So, well, that's it. So these are the references, and thank you very much. We continue with the next now questions, and then the next and last.
Okay, thank you, Dr. Bielza. And let me check if there are some questions. Yes, we had one question. Why do you adapt one to the decimal representation of the class?
Yeah, this is related to the binary, to the label power set method, where you have many classes, and then you convert this problem into only one class. So how to do this? This is a matter of enumerating all the possible combinations of all the classes. And then in this case, I was the zeros I think that there were four class variables. So I assigned 0, 0, 0, 0 to number 1, and then 0, 0, 0, 1 to number 2, up to 1, 1, 1, 1, number 16. So this is just a way of enumerating all the possible combinations of the classes in some manner. So in this case, decimal representation minus 1. So this is what we decided, but this is it's not important. It's just a way of enumerating all the possibilities. I added in the chat for Enrique Sucar the paper we were talking about complexity of Bayesian network classifiers of the algorithms. It's a paper published in Journal of Machine Learning Research in 2016. So you can see it in the chat.
Okay. Thank you, Bielsa. Well, we start with the third part of the tutorial with Bojan, sorry.
Bojan Mihaljevic, yeah.
Bojan, do you prefer to put the video or you present in live? Bojan?
I don't see Bojan.
Okay.
Yeah, because I think he thinks that he will go. Bojan is there. Yeah, but he's muted.
Your microphone, Bojan.
Microphone, Bojan.
Now
We can't hear you.
Okay.
muted, but it's not muted anymore. Can you
Yeah, we can hear you, but
hear me now?
not very well.
Okay. So
yeah, now it's fine.
In my case also, okay. So in my case also, you have the video. So if unless you, I don't know, want me to say something about my part of the tutorial, you can start playing the video, and then I'll be there for the questions at the end of the session. So in around an hour or so. So is that okay, or should I introduce my part in some way?
You prefer?
Okay, well, so so this is really we're using 1R package to be in classifier. First part I'll be showing mainly there's a second part where I use some detail on a particular data set to illustrate concepts that are relevant if you're interested in say going into some details about all of, and because of the time constraints, I went through the second part a bit quicker in the slides. So, but still, it's all in the slides. You have a lot of slides. The code is already shared, so you can download it and go along with the examples. So, yes, I'll leave you to the video. I'll be ready to answer questions that I have.
Yeah, because the connection is not very well, I think, Bojan. You are, from time to time, you are freezed.
Will you put the instruction for the load Earth software?
The instructions on during the weekend, so I hope they have been shared with the participants, and if
hello and welcome to the
right, so it's also in the slides, but there's a PDF that I sent out with the instructions.
Okay, I will put the
practical part of our tutorial on Bayesian network classifiers. So I'm going to start right away and going to open up the slides. Okay, so today my goal is going to be to introduce you and to present you the BN Classify R package. So this is a package for learning Bayesian network classifiers from data. So first I will introduce the functionalities that this package provides. I will show you the main functions and show you some typical examples of how it's used. And then I'm going to go into some details with the data set. So we're going to be using one synthetic sort of a toy data set, which is suitable to illustrate some concepts that have been covered already in the theoretical parts of the tutorial. So we'll focus on unidimensional classification. I won't be talking about multidimensional. And importantly, there is so you should have already received the installation instructions. So there is a PDF with installation instructions. So regarding how to install all the R packages that you are going to need. And that script also contains all of the data and all of the code snippets that I'm going to use. So there will be a lot of code in the slides. And since time is so short, I'm not expecting you to follow along by coding and writing it yourself. Rather, the code is already provided in that script. So you will be able to, if you follow the instructions, you'll be able to have it all loaded by the time that I begin, and then you can basically run the same lines of code that I'm going to run. And in some cases, you will need to uncomment something and complete the code. But in any case, there is really not much time, and I want to cover a few topics. So the idea is not really that, I mean, if you cannot follow along during the talk, it's not, I guess, too bad, because you will have the script and you will have the video, so you will be able to go through it again afterwards. So my main goal is really to show you the package and really to do a sort of a demo myself. And if you can follow along, that's an added benefit. So really regarding that part, like the setup, if you haven't received the installation instructions, so this is really the instructions. So I'm expecting you, if you want to do this, to replicate it, to have R installed. You may optionally have R Studio installed, which is what I'm going to be using during this demo. And there is this particular zip file that if you have downloaded it, then you have everything already at your computer that I'm going to use. So, so this zip file contains both the data and, as I said, a script with all the code that I'm going to run during the tutorial. And also it contains a script, this install packages script, that will install all of the necessary packages. So again, if you have received the instructions and if you have followed these sort of few lines of instructions, then you will have everything ready to follow along. So this is just sort of what is already in the instructions. So then, importantly, in the zip file that you have, there is this particular workshop.r file. So this is the script that contains everything that I'm going to use, all of the code. So it's all there. And what I'm going to do, I'm going to create a project in our studio in this particular folder. And this is what I recommend that you do as well. So I'm going to go ahead and create this project. So I have our studio opened here. So I'm going to create a new project in an existing directory. So this is my folder where I've unzipped the content from the link that I showed you, the bit.ly.link. So this is the zip file here, and I've unzipped it here. And it contains, as I said, data and a couple of scripts. So I'm going to be using this folder to create my new RStudio project. And once I do, I'm going to open up workshop. I think it's here. Let me see. Workshop.r. And this is really a script with, as I said, all of the code that we're going to be using. Okay, so let me go back to the slides now that this setup part is ready. Okay, so first, as I said, I'm going to introduce and talk about the package from sort of a more overview type of approach, really to go through everything. And this is what we're going to do now. So in a summary, this package, Bayesian Classify, implements state-of-the-art algorithms for learning discrete Bayesian network classifiers. So we're now focusing only on discrete variables, which is really the most common setting for using Bayesian networks in general, not just classifiers. And well, the package provides function to learn these classifiers from data, as well as to, of course, use them to predict, and some functions to assess their predictive performance and plot the network structures, etc. Some utility functions. And throughout the entire tutorial, we're going to be using one dataset. So it's this car evaluation dataset. So it is, as I said, a toy dataset. So it's a synthetic dataset, which is really handy for some of to illustrate some things. So it is a dataset with. So here I'm printing out the dimension of. So this car object contains the data. Again, I'm really, of course, I'm assuming some basic familiarity with R, so I'm not going to be explaining sort of what the data frame is and things like that, but that's also the good thing is that you have the script already and you can just run it. You don't really need to understand everything underneath. But basically this car object here is a data frame, so it contains data. So by printing out here, well, I can see that it contains 1,728 instances and 7 columns. So that's in this case, that's 6 features or 6 predictor variables and 1 target variable or 1 class variable. So basically, what we want to do is, so we have car properties or car features, such as the buying price. So here we have the buying price, which can be either low, medium, or high, or very high. And then we have more features like maintenance price, or the number of doors, like 2, 3, 4, or 5 or more doors. And what we were interested in is the class variable here, which we cannot see it here, but I'll also explain it later, which is really whether sort of how good is the car. Is it unacceptable? Is it acceptable? Is it good or very good? So there are 4 classes, so 4 different classes. And it's also repeated here, unacceptable, acceptable, good, very good, that we want to predict from these features. So again, if you would run this in R, this question mark car, you will get more information about this particular dataset. So also importantly, what I've done here, I've loaded the package. So if I do this, library Bayesian Classify, I'm loading the package. So all of the functions of the package are already in memory, and then I've loaded the data. So if I go back to the script, so it's all here in this first couple of lines. So if I just, sorry. So if I just go ahead and run this, it should work, right? So this is the same thing that we saw in the slides, right? So now we have the data in the package loaded. Okay, so basically there's sort of 5 different steps, or when using Bayesian Classify, we can talk of these 4 different steps, perhaps in in our as a user of this package. So one sort of kind of a task that we can do, or sort of a step, is to learn network structure. So that means learning the graph. So all the different structures and classifiers that you learn, like whether tree-oriented or naive Bayes, etc. So that would be learning structure. And this is sort of relevant because learning parameters, which is sort of the next step that we need to do to really fully specify the model, is separate. So those two steps are separate in being classified. So then the other step would be to actually learn the parameters. So now we have a structure, and we want to complete it with some specific parameters that, again, fully specify the model. So another sort of task that we may want to do is then to evaluate the model that we have. So we have a model, and we would typically be interested in, for example, predictive accuracy. And of course, it's quite somewhat trivial, but it's fundamentally we want to use the model for predicting. That's typically a goal that we have when learning classifiers, and in general, and Bayesian network classifiers in particular. And also, of course, you can, as you go along, you want to look really at the model inside. You want to plot it and print and find out and query it about some of its properties. So this is a quick example of how those 4 steps or 4 tasks can be done in being classified. So basically in 4 lines of code. So this is really how the package has been split according to their functions corresponding to those different steps. So here, for example, we see, so this is our car object. So if you remember from the previous, one of the previous slides, this is our data frame. So this object here, car. And this is the name of the class variable. So again, if you recall, the name of the variable that we want to predict was class. So here we're actually saying, okay, I have the car data set and I want to predict this variable, and this NB here means, so give me a naive Bayes structure. So basically this function will give you a naive Bayes for this data set with using this column as our class variable, as our target variable. So it says this learns a naive Bayes structure. And then we have in this object here in NB, what we have is a naive Bayes structure for this particular data set. So then the next thing that we can do with this naive Bayes structure is to learn parameters. So basically we want to fit parameters. So for this, we have this LP function, so learn parameters. So then LP, we're passing our structure. So this is our structure, our naive Bayes structure. So it's this object from here. Again, we have the data set. So we need to learn the parameters from some data, and this is the data set that we're going to use. So we're using, of course, the same data. And we have here this smooth parameter that I'm going to explain later. So this has to do with Bayesian parameter estimation. So for now, we can just say that there's this particular parameter that we always need to specify when calling this LP function. So this would be 2 steps, right? Learning structure and learning parameters. And this here is an example of cross-validation to assess predictive accuracy. So here, we're calling this CV function for cross-validation. We're passing our object here. So now, notice that this object here already has parameters. So this NB here has already been assigned parameters. So we now have a complete model, both structure and parameters, and we want to evaluate that. So we're passing this object here. Again, we have the same data set, so we're going to be using this data set. In this case, the number of folds that we're going to be using in cross-validation, right? So here I'm saying there are 10 folds. K is equal to 10, so this data set, this car, is going to be split into 10 folds, and that is going to be used to get this estimate of accuracy. So I'm not specifying what measure I want to use, but implicitly, so it's implicit in this function that we're going to be estimating accuracy. And here we get a number, right? So the number that we're getting here is 0.85. or yeah, 0.86 if you want to round up. So basically the accuracy of the naive Bayes on this data, or the estimate of its accuracy with 10-fold cross-validation, is 86%. So 86% instances are correctly classified by naive Bayes, right? So this is the number that we have. And of course, as I said, one basic and simple, yet basic and important functionality is the prediction. So now we have our model and we want to predict the class label on some new data. So we use it with this sort of standard R function for this type of things called predict. And what we need to pass again into this function is our classifier, our object. So MB, again, this is both structure and parameters because we've set it here, and the data that we want to predict. So here I'm just predicting it for all of our entire data set, right? For all of the data. And here what I'm getting is really a vector of class labels for each of the instances, right? And I'm just printing the first 6. And the prediction of the naive Bayes for the first instances is that they're all unacceptable, right? So this is what naive Bayes is giving us. So as it says here, so while there are multiple alternatives to MB for the first step, you are most likely to use LP, CV, and predict for steps 2 and 4. So mainly what we're going to be talking about in this sort of first part of the presentation is about alternatives to MB. So there are, of course, as you've seen already, alternative structures. So it's not just a naive Bayes. So there's 3 augmented naive Bayes, there's a semi-naive Bayes, there's a different kind of structures. Some of them we're going to see, some not. And really, that's really the part where you may have most flexibility, right? So, or maybe the most interesting part. Then the remaining parts, learning parameters and cross-validation and prediction, are pretty much straightforward, and there's not much to think about or to really choose, not too many options to choose among. And so basically this few slides were sort of a quick overview of the main sort of, as I said, steps that can be done. And now we're going to go into some details, right? So I haven't really explained the different options that you have in the different functions, so on. So we're going to go a bit into that now. So the network structures that are supported by Bayesian classifier, or that Bayesian classifier can provide, are the following. So currently, so we have naive Bayes, of course. So we have one dependence estimator. So if you recall this from the theoretical part, so this is somewhat more complex than the naive Bayes, and this includes the 3 augmented naive Bayes and the 4 augmented naive Bayes. So basically, these are classifiers or augmented naive Bayes models where each feature can have at most one other feature as a parent, right? So so it's a 3 augmented naive Bayes if there's a tree among the features, and it's 4 augmented if basically if it's less than a tree. So if there are less arcs than n-1, where n is the number of variables. There's the k-dependence Bayesian classifier, or basically, so if this is one dependence, so k-dependence would be allowing up to k parent features for each feature. There's semi-naive Bayes, and there's the average one dependence estimators, which is something that I think Pedro has not covered. And it is perhaps similar to multi-net in the sense that we have more than one structure. But again, it's built quite differently. But since it wasn't covered in the theoretical part, I also won't be going too much into this, into particular this model. But it's good that you know that it's also one option that you can use with the Bayesian classified package. So in a sort of a summary of all this, since we saw all the different structures, So there's pretty much, so for each structure, so these are the different structures that I just talked about. So the naive Bayes, or tree augmented, forest augmented, or semi-naive Bayes. So for each structure, there can be one or more learning algorithms, right? So for naive Bayes and for AOD as well, there's really no search involved. So sort of we can already know beforehand what the structure will be, right? We only need to know the names of the variables and we know what the structure is. And for the other structures, generally we do some kind of a search. We have some algorithm to decide what the particular instantiation, or say, of that type of structure is going to be. So for the sort of this one dependence estimators for tree augmented, forest augmented, there is a couple of algorithms, or actually there are three, right? So the basic one here called CLODE. So the CL stands for Chou-Liu, and this is sort of the standard tree augmented naive Bayes that Pedro has most likely told you about, right? So this is a model that maximizes the log likelihood, right? So this is the TAN, the tree augmented naive Bayes, with the highest likelihood among all possible TANs. And then we have other algorithms. For example, we have this TAN hill climbing algorithm, which is sort of a different approach, which is where we learn the TAN structure by sort of optimizing the accuracy of our model. So we're not optimizing, in this case, log likelihood, but the accuracy, which is probably sort of more suitable to our goal, right? More because we usually use classifiers to predict one particular variable, not to fit the entire joint distribution. That generally not the goal. So then basically, as you see, so we have different algorithms, and for each algorithm there is one function. So here, so for naive Bayes, we already saw NB, right? For this particular Chou-Liu, we have this function here, so it's TAN CL. For this hill climbing TAN, we have TAN HC. For this hill climbing superparent, TAN hill climbing superparent, etc. So the point, sort of main point for this slide is that there is one function. So if you can go to this table and say, okay, I want to learn the TAN with Chou-Liu, well, I have to use this function here. And then, of course, there's other options. Sometimes you can use different scores, and that's why this function sometimes will have different options. And we're going to see some examples. So basically, as I was saying now, so there is a function for each different algorithm. So basically, what you need to pass to these functions is the name of the class variable and the data set, and then you have the optional arguments for that algorithm. So, for example, so here we have this code here, which is going to use this standard TAN that I was just talking about. So we have TAN CL, we have the name of the class variable, we have the data frame with the data, and we have the score that we're going to use. So I'm going to talk about bits more about the score as well later on, right? So this here now gives us a different structure. So before we had a naive Bayes, now we have a TAN, right? And here we have another model. So here we have a semi-naive Bayes, this object here, FSSJ, learn with this function here, FSSJ, and again, the same two arguments at the beginning, the class and the data, and then some particular arguments for that algorithm. So I'm not going to go too much into now the different options for all of the different algorithms, but if you remember this from the previous part, so basically for the semi-naive algorithms that Pedro talked about are all sort of optimizing accuracy or some sort of measure of prediction. And we usually want to, while learning, estimate those measures with cross-validation. So not on the training data, because otherwise you would have gotten a very complex semi-naive Bayes. Basically, we will have a complete graph among the features. So this K here is for the cross-validation. So how many folds are we using internally while learning this semi-naive Bayes? And this really has to do with stopping criteria. So if this were positive, if this was a positive number such as 0.1, then we would keep searching. So the algorithm would keep going until the improvement in the score was not larger than 0.1. And here, since we have 0, it means that if the next model is as good as the previous one, it's going to accept it and go on with the search. So there is a lot of documentation in the package that explains these functions and the options that you have. So basically, there's some vignettes that maybe I'll have time to talk about at the end. If not, you can really just run this code and open it. So basically, if I wanted to run this snippet here, I should already have it. So this was the previous part, right, that I had. So really, if I want to run that, so sorry, see if this is okay. Okay, so this is the previous part. So here I'm learning the tan, and here I have the semi-naive bias. So I'm already sort of really just run this code that I have here. Okay, so really what we get back when we run these structure learning algorithm functions such as MB and TANCN are objects. These are our objects, and their particular class is this one. It's B and C for Bayesian Net Classifier, DAG. So basically saying that there's a structure, right? So it's not a full model, it's the DAG. So once we have that kind of an object, we can do a couple of things. So really the basic thing is really to print such an object to console. So we can print it out. So for example, if I go here and I take this tan and I just print this, I get some information, right? So I get the name of the class variable, I get the number of features, there are 6 features, how many arcs are there, there are 6 arcs in the network, and which learning algorithms was used to obtain the structure, it was TANCL. So there's some basic info that I can get, right? So it's also shown here. And we also get to see the class, right? So that's a network structure without parameters. And also perhaps it's more interesting that we plot the object. So we can use this also against standard R function for plotting. So it's called plot, and we just pass our BNC DAG object and we just plot it, right? So this is the plot of our tan. So it really looks as expected, right? So the class is the parent of each features, and there are arcs among the features. So if you have 6 features, there need to be 5 arcs among the features. So if we count them, there's 1, 2, 3, 4. There's somewhat less because we used a different score, and I'm going to talk about it in the second part, right? So we didn't maximize likelihood, but if you recall, I've set an option when learning this called score here, and I've set this particular score. So this is the reason why we don't have 5 arcs here. Of course, plotting, it may not look right. For example, if you have too many variables or something, but there's options that you can use to sort of tweak it a bit so it can look better. So there are some options like the layout type, how you can so this is sort of a different location or layout of these nodes and arcs in the plot, or the font size, so how large you want the letters to be. So these are options that you have in this plot function in BNC. So if you want to use these options, well, you can type this, right? !plot.bnc.dag, and you will get the help for this function. So how to plot a network with some different options, changing something from the default setting. And of course, printing is nice. For example, if the network is not too big, but if you have really many variables, sometimes it might be hard to make the plot sort of easy to see, right? To understand, and then it's easier sometimes to extract some information by really just the console, by typing something, by working really with say with the object. So you may want to ask what are the parents of certain variables because you're interested in some dependencies among the variables. And one function like that can be useful for this is this families function. So it gives you all of the families in the network. And the family is sort of a set comprised of a node, any node. So you have a node, and the family of that node is itself plus its parent in the graph. So that would be a family. So basically the family of the buying node is itself buying and the class. And the family of the maintenance price node is maintenance price, buying price, class. So you can see this is also a way to see dependency, one of the many options that you have in the package. Also another representation that can be useful in R is this sort of compact model string representation, which I'm not going to sort of explain its syntax, but basically it represents its entire DAG with this syntax with brackets and these, what are they called, like bars. So basically you have all of the nodes here, and basically what this is saying, class is a parent of buying, and class has no parents, and class is a parent of doors, etc. So this is also, if the plot is too complex, you can print this out and get an idea about the structure. Or for example, you can use this function narcs to see how many arcs are there in the structure. So you get that there are 6 arcs. Or you can, for example, you might use some algorithm like the semi-naive Bayes algorithm that can provide you sort of, provide the semi-naive Bayes, but it may also end up being a very simple structure, like with very few arcs. You may want to ask if the structure is really a one dependence estimator. So you have this type of function. And so here, if you pass the TAN object, you see that this is one dependence estimator, and it's not a semi-naive Bayes, right? So you have this sort of utility functions, right? And there's a number of these type of functions that you can use with this BNC DAG objects, and you can sort of find out how to use them if you read this particular help. So you go question mark is spelled BNC DAG, and you will get some information about it. So if I just show you that quickly, so it could be, yeah, so here it's here, right? So we get the list of functions that we can use, right? So we can get the list of I don't know, certain basically the functions that we've seen, right? What are the features in the model, and so on. So that's sort of working with the structure. But as I said before, a structure lacks parameters. So really, we cannot, for example, use it for prediction. It's not a really fully specified model. So we need the parameters. And there in Bayesian classify 3 parameter estimation methods. And for all of them, you're going to be using just the LP function. So there's a Bayesian and maximum likelihood estimation. So they're sort of one method put together. And there's a sort of average weighted naive Bayes and another method, which are sort of a bit more elaborate. And I'm not going to go into them because they were not covered in the theoretical part, but you have a lot of information on them in the documentation of the package that I'm going to sort of point you to at the end of the tutorial. So in a summary, they work a bit differently. So this second method, it sort of uses a discriminative approach. So it tries to improve the prediction of them. So it learns the parameters not by maximizing, for example, likelihood, or not by Bayesian estimation, but trying to improve a bit the prediction of the naive Bayes. And basically it works sort of by weighting features. So Pedro talked about feature selection. So this is a sort of more general approach when you give weights to the feature of the naive Bayes, right? And this second approach is to do with feature selection. So so this sort of feature selection in terms of code is very simple. So we have the LP function, and we just need to pass the network structure as we saw, and the data set, right? And then we have to perhaps give some arguments for this function. So here are examples of how to use all of these methods, right? So LP, we've already seen it with the smooth parameter for Bayesian parameter estimation. So basically, this parameter that I didn't explain before, but I believe Pedro has talked about it. So basically, it's really it's used for if we were to set a 0 here, it would be maximum likelihood estimation, right? So it's a hyperparameter for this prior distribution that we are using on the parameters that we are using in Bayesian parameter estimation. So we need to have a prior, and we're actually specifying the prior by means of this particular parameter. So we are assuming a Dirichlet distribution for the parameters, and with a single hyperparameter, which is this particular number here. So really the point here is only that this be a small positive number, right? So if it's 0, then it's just maximum likelihood estimation, and you basically generally use just any small positive number. And these are the options for the other two methods, right? So which again I'm not going to talk about for reasons of time, but you can read about it in the documentation of the package. And there is one function that you can use really to combine structure and feature learning all together. So if you want to put the two steps together, not separate, so it's called BNC, Bayesian Network Classifier, and then you pass the name of the structure learning algorithm, and basically that's it. Here we have the arguments for structure learning, and also you could have arguments for parameter learning, and it's all done together, right? And here you get your model. And then this LP function and this BNC function return somewhat different type of objects. So this is now an object of class BNC BN. So BN as say a fully specified Bayesian network. And now we can do other things such as prediction, for example. So for example, if we print out the object now that we also have learned parameters, we also get as output the number of free parameters in the model. So this is how many parameters have been estimated from the data in this TAN model. So in this case, well, 131, right? And also we now have with discrete data, we now have these conditional probability distributions placed in these CPTs, right? In these conditional probability tables, right? So we have for each value of the class, so for this value and this value and this value, we have one distribution. We have the distribution of this feature for this class for the unacceptable cars. So this is distribution. For acceptable cars, this is this other distribution, and so on, right? So in say in very good cars, the buying price is mainly low. So apparently it's very good from the perspective of the client. So if it's not too expensive, then it's good. And some are medium, and obviously in this case very expensive cars are not really considered very good. They're probably considered too expensive, right? And so if you want to look at these CPTs, we use this params function. So we have a params function. We pass our BNC BN object, in this case the naive bias, and we access the CP. So here we get the list, and this is typical accessor function for a list in R, and then we use the name of the feature, right? And then we get back the CPT. So again, this is all in the script. So if you're not very much familiar with R, well, basically you can just run this, and then you can try to say understand what it is about. Okay, so I guess this is here, right? Params here. So yeah, this is what we have been talking about in the slides. And yeah, we can use this function to get the number of parameters. And again, as before, we have all of these utility functions grouped in this particular, say, help file, question mark, inspect, BNC, BN. And then we may want to evaluate the model. So one sort of way to evaluate different models is sort of to compute scores So there are these typical scores that are penalized likelihood scores or log likelihood scores, such as archaic information criterion that we used before when learning the TAN, or the Bayesian information criterion. And we can compute this simply from the data with these also standard R function, log, lig, and AIC, and big. So we get values for these particular scores. And perhaps more importantly, so these are scores really related to the to the joint distribution. So say how well we're fitting the joint distribution. And more related to prediction, we have accuracy, right, or the percentage of correctly classified instances, and we can get that with the accuracy function. So here we use predict to get a vector of prediction. So P is a vector, and then we just compute accuracy, and we also, besides the prediction, we pass the vector of true classes, right? And then we get our number, right? So before it was, I think we had something like 85. So with cross-validation, I think the estimate was like 85%. And when computed this on the training data for the naive Bayes is it's 87. So also, as you can see, it's basically not higher than what cross-validation told us. Even though we're getting this from the training data, and it's basically because the naive Bayes can really hardly overfit the data. So it would have hardly gotten, say, 100% accuracy, and then cross-validation would show 70%. That sort of would be very hard. So it would have to be a case when you have really, really little data, so that the naive Bayes would overfit, because it has basically really few parameters that we are estimating. And so yeah, this is this accuracy function, and we have CV function, right? The CV function that we already saw. So it's stratified cross-validation, right? And basically all we need to do is say the number of folds that we want to use. So we just say CV and the number of folds and so on. And also, yeah, one detail is that it's perhaps a bit technical, but you may sort of evaluate the entire process. So you do structural learning, that's one step. Then in the next step, you learn the parameters. So when you call CV, CV is going to repeat both steps on all of the training folds. So it's going to learn the structure in the same way that you did, and then when you created the object, and then the parameters in the same way. And it's going to do that k times. And also you have the options to just, so for example, to have a fixed structure, right? So if you say here Doug false, then the structure will not be relearned on each training fold. So you're just going to be relearning the parameters. So if for some reason you have a fixed structure and you want to evaluate really the parameter learning part, so how well is that working, then you can use this option. And again, yeah, you can get back sort of the vector of the accuracies per each fold, or you can get the mean accuracy, and well, you can use this and then to get the standard deviation and so on. So basically, as you can see, this is a TAN model here, and its accuracy is quite higher than that of the naive Bayes, right? So it's in the range of 94, 90 something in any case, whereas naive Bayes was around 85, 86. And also, you can cross-validate more than one model at once. So you can use the same partition of the data into the folds to really evaluate a number of classifiers, right? So here, in the same function, you can pass a list. So you can pass the naive Bayes and the TAN, and then get back a result for each of them, right? So here we see sort of the results, right? 86 for naive Bayes and 93 for TAN. And of course, there's really a lot of options generally in evaluation, right? So BN classifier provides sort of some basic functions with CV, but if you want to use, I don't know, area under the curve or many different metrics that you might want to use, then there are packages which are really made for that, right? Tailored for that. So these are basically these meta packages, such as Caret or MLR. And you can use BN classify with those those packages to do that, like to estimate accuracy. So BN classify is integrated with Caret and with MLR, and it can be used like different classifiers from those packages. So in particular for MLR, you need to call some functions just to make it work, but it's there's a lot of examples in the package. So for example here, I'm not going to go into detail, but basically with this function we convert our TAN into an MLR classifier, and then we use it as an object as any other MLR object, right? And so that's what it says here. It behaves like any other MLR classifier. So for example, here what I'm doing with all this code, which is now MLR code, this is not being classified. I'm comparing our TAN to a random forest. So on this data set, for example, MLR is telling me that the accuracy, mean accuracy for a TAN is this, 93, and for the random forest is 96, right? And the thing about MLR, you have many different resampling strategies. So it can be cross-validation or bootstrap, or you can use different measures, etc. There's a lot of flexibility. And the same with Caret. And then in prediction, so we've already seen that the sort of only option that you might care about is this one, probability true. So we might, instead of the class labels, we might want to get back the probabilities, right? So basically, if we set this argument here, so what we're getting is for each instance, we're getting a distribution, right? Say the posterior distribution of the class given the features, right? So for example, we can see here that the naive bias is really quite confident, right? So basically, it's almost certain, right? It's assigning virtually 100% probability to the unacceptable class label for these 6 instances here, and we're going to mention this a bit later on. And there are also a number of other utility functions. So you can convert BN classify objects to objects from different packages, such as graph or GeneRain, and this can be useful for different tasks. So I'm going to go a bit faster now through this syntax. You can go back to the slides and check it. I want to go a bit to get to the case study and to talk about it in some detail. So I'm not going to talk now about the specifics of these examples, how do you convert to GeneRain object and so on. And there's also some other utility functions in the package that, again, I'm not going to stop and talk about now. And really just to mention this here, so Pedro talked about selective naive bias, right, about feature selection. So also this type of task is really best handled with specific packages. So packages done for that. And again, sort of the right packages for that are packages such as MLR and Caret. And again, it's best to use them. So this is an example here of how to use this forward feature selection with MLR and with TAN. So it's sort of, again, this is MLR code that you may want to come back and look at it. And yeah, this is an example of feature selection. So it's all in the slides. It's also in the script. So really, you can run this yourself. And basically, as I said before, there is a lot of documentation in the package. So I've tried to give an overview, but for details, you can look at this. Well, at the first place, you can look at the paper that we've published, sort of describing the package in the R journal in 2018. And then there are a number of vignettes in the package. So you can just type a vignette, say overview, package being classified, and you will get, you will open this vignette with this sort of, gives you one side of say of the story. So it gives you an overview, and there are some are more technical, such as this one, methods, and and so on. So really, this is just running this code, and you can anyway, so I'm not going to copy it now, but you have all this code. So basically, just in a summary, so this is a package which is it's been on CRAN now for 5 years, and it's relatively efficient. So some parts have been implemented in C++, so it's not as slow as our packages can be. And yeah, I hope you can try it out and find it useful. And I'm looking forward to any kind of feedback. And so there's sort of this GitHub where you can post any kind of feedback, issues, and so on. And there's also some work in progress, like multinets that Pedro talked about, and Gaussian features that are in particular branches. So if you feel like trying that out, you also please go ahead and you can try it out. And again, all feedback is welcome. So now that I've gone through the functionalities, which is perhaps, say, a less interesting part of the tutorial, I want to go into some details of how we can work with one particular data set with this package. So in this current evaluation data set is interesting because we have actually relationships between the variables that we can actually try to see with the Bayesian network, right? And basically, our class variable, which is car acceptability, is a function of some latent variables, that we cannot observe. And these two latent variables are price and tech, like technological part, right? So price is really made up of buying price and maintenance price. So that's why, if you recall, TAN had an arc between buying and maintenance, because those two features are very related. So if generally, even within cars of the same class, if buying price goes up, well, the maintenance price perhaps goes down, but there is a dependency. And there's also this second variable where we have all of these different variables that are sort of involved, so including safety and the number of persons that can fit and so on, so making this comfort latent variable. So yeah, we know all the variables are discrete. So yeah, so we get a naive bias and we plot it, and we see this, right? So basically what the naive bias is telling us is that, or the model what assumes is that the features are independent given the class, right? Not marginally, which is a common mistake. So in general, the buying price might be increasing with safety, but within cars of a particular class, we're assuming there's no dependencies. And so then, for example, so these are sort of examples that you can run and work with, right? So if you learn this, so what is the class prior probability, right? We estimate the parameters. Well, how do we get that, right? Well, we go to the params function, and then we access the class element of that list. And we're getting here what it's called the class prior probability, or the probability of a class when we're not observing any particular features, right? So the most common type are these unacceptable cars. And so basically inference here is really easy, right? So I'm just going to go skip this. So this is an example how you could compute the class posterior by hand if you wanted to. So you would just access the CPTs and you would just multiply the entries and you would get this, right? So this, once you multiply it, you really need to just sum over it, right? So what you're having is the probability of the feature and this particular class, and then you just need to sum over to get the class posterior. So this is an example here how you could do it by hand. And again, what we see is, for example, we're getting, as I mentioned before, really a lot of really certain output by the naive bias, or in other words, we're getting zero probabilities. So for example, why do we have these zero probabilities? So we can, I know why, and it's related, for example, with this buying feature. So if we look at the CPT, so if we look at the CPT, so if we go here and just say, so it's already here. Yeah, but we'll need to repeat this. So if you see here we used smooth is 0, right? So the smooth argument is 0. So we need the structure. Right. So basically what we see, there are some 0 entries here in our CPTs. And then, of course, we multiply these entries as we are here. We're going to get some 0 probability. So basically, that's really the motivation, or one motivation for like never really using maximum likelihood to estimate parameters. So we can use Bayesian estimation with just some small smooth value, and then we'll not get these zeros, right? And so basically what we'll need to change here in this example is this here, and then we won't be getting the zeros. And then if we multiply again, we'll be getting, well, at least not zeros. Anyway, again, the naive Bayes is really, really confident in this case, but for example, not really so much. Anyway, these are different instances, but at least we're not getting 0 probabilities for the classes, which can be problematic. I'm not going to go into detail, but basically a 0 is going to really sort of erase all other evidence that you may have in favor of a particular class. And so yeah, we can, this is some example like how we can compute, well, make the confusion matrix, well, get the accuracy. And like if you wanted to go into some details, for example, we can ask, for example, whether this particular doors feature is independent of the class. For this, we can use the bnlearn package and the CEI test function. So if we do it, doors, right. Right. Yeah, so yeah, so the hypothesis of independence is really not really rejected, right? So we don't really reject, we get 0.3, yeah, 30% say for the p-value, and we're really not rejecting independence here. So we can really say that this feature is independent. It's not useful for prediction. So if we removed it, so the question would be whether naive Bayes would perform better or not. So now, because I'm running short of time, I'm not going to stop and go through it, but basically it doesn't really affect naive Bayes. So naive Bayes is not affected by irrelevant features. You can add as many of them if you want, like if you have, again, there can be some noise, but basically it's not a problem. The problem with naive Bayes is redundant features, right? So here again, I'm going to go through it very quickly because it's almost an hour now. But the example here that you have in the slides is really, I'm taking one feature here, which is safety, and I'm copying it and adding it to the data set. So I'm adding a perfectly correlated variable, right? So which is, there's like now the independence assumption, the class condition independence assumption is clearly violated. So now if you would go and run this code, the result would be, I think, that it's really not really degrading naive Bayes, right? So there can be some violation of this independence, but it wouldn't really affect naive Bayes, right? So the probabilities might be really not well calibrated, but it might not affect too much the accuracy, right? Because then the probabilities doesn't matter too much as long as the ranking, or as long as the top ranking class is always at the top, right? So we'd added the copy here, so our probabilities are probably a bit less well calibrated, but it works pretty much similar. But now I'm adding here 10 copies of this variable. And now really what you see if you run this is that it really goes down, right? So the accuracy really goes down, right? Because basically what happens with naive bias, or in this case, right? Basically, we have 11 safety features, so there are 11 versions of the same equal features. We have 5 other features. So basically, we're giving much more weight to this feature, meaning that we're sort of ignoring some useful information in other features. So basically, the problem with naive Bayes is really one problem is when you have really redundant variables, right? So there are 2 approaches basically to do this. So one is feature selection or weighting, and the other is to introduce arcs, right? To have all of these augmented naive Bayes models and to really account for these dependencies, right? So in principle, you may want to choose the former where you don't have much data, right? You have really few data, you cannot fit too many parameters well. So you may go for a very simple model and really remove some of the features from a naive bias. Alternatively, if you have enough data, well, you will go for adding some arcs. So basically, if you don't have too much data, you might stick with a somewhat simpler model like a TAN. If you can afford more, you might go for a more complex model like a KDB or sometimes a semi-naive bias, etc. So that's really roughly sort of the kind of trade-off that you want to work with. So basically, this is again an example of learning a TAN on our data. So this is a TAN, and you can see that really the arcs here sort of correspond to these latent features that we see. So here's price, the latent features, buying price, and maintenance price. And there was the other sort of more technical features are also on this other side. So it makes sense, right? So here we're not using a score, so this is maximum likelihood TAN. Again, so there's sort of many details that you can go in here. So for example, doors was independent of lag boot given class, right? Doors was also independent of class, as we saw, but in an augmented naive bias, we always have that arc, right? But for example, the reason why we have an arc here, even though it's independent, because a TAN will always introduce 9 minus n minus 1 arcs, right? So even if doors is independent of everything else, there will be an arc. So that's the reason why scores like I can be useful, because they can sort of remove the arcs that are not really useful in a TAN. So again, since I'm running quite short, I'm going to sort of run through all of this just to really tell you what it's about, because there's a lot of examples in the slides, and then you can sort of go back to them on your own and work with them. So this is a bit about this IKE and BIC scores and how actually what are their values in a TAN. And yeah, this is a difference. So if we use IKE, for example, there are no arcs with doors. Doors is really independent of everything given the class, and there are no arcs. And yeah, so basically these are just some questions that you can use as a sort of an exercise if you wanted to work with this. And as an example, BIC is really not adding any arcs. So BIC penalizes more than IKE, and it's not really adding anything. And it's also perhaps an example of how some, say, generative scores that really are related to the joint distribution, yeah, perhaps not always very suitable to a classification goal, right? To something that's where goal is discriminative, right? And yeah, so let me just go through this. Yeah, this is an example of a TAN with discriminative learning by maximizing accuracy. So again, it's similar, and actually there's now an arc between persons and doors because it's improved accuracy. And here, if we print this, we can see how score evolved, right? So we started with this score for the naive bias, and then it jumped to 90%, and already with 2 arcs, it was practically a 94%, right? So yeah, if it also depends on our epsilon, right? So if our epsilon had been much stronger, it would have stopped in naive bias. So with an epsilon of 0.3, it just stopped at 2 arcs. It added this arc and this arc. So these were the 2 arcs that most improved at the beginning, right? And yeah, of course, if you run this, you would see that these discriminative methods, or as I say here, wrappers, are slower, so they take more time, considerably more time than, say, Cholio. But again, it's not really too slow because, as I said, of C++. And yeah, you can really see examples of this backward semi-naive bias. So this one is a semi-naive bias where you start from the naive bias and start removing features and adding arts, etc. So yeah, I'm just going to also, this is about the feature weighting. I'm going to skip. And basically, what you have here, I'm also not going to stop, is a bit of an overview of the packages that you have. A very important package for Bayesian networks is BNLearn. So there's a lot of functions there that are useful, but it's not really tailored to classification, but there's also some classification models. And then you have a number of other models that you use for plotting networks and for inference and so on. And most of them are listed at this graphical models task view, which is this link that you have here. And here's also a list of useful functions that you might find if you work with this. So I'm just listing them here. And also, well, how you can export into other formats or serialize your networks. There's also a lot of data sets and synthetic networks, for example, in BNLearn, which you can use for if you wanted to work with Bayesian networks. And well, this is just a list of free software in general for Bayesian networks that you might find useful. And again, this is a repository in general of Bayesian network models, which you might find useful. And in summary, that's it. So there's, as I said, a lot of content in the slides. There's the script, so you can really try to work it through. So they're really, I think there's something to be understood about Bayesian network classifiers if you go a bit to this, especially to this second part, this case study, which I've gone through a bit quickly. And I thank you for your attention, and I'm looking forward to all of your questions, both now and of course later on. If you keep working with these scripts and with these slides, any kind of questions and feedback that you might have, they will be very much welcome. Thank you. Hello?
Hi.
Can you hear me now?
Yes.
Okay, great. So yeah, that was the video. Again, thank you once again for your attention, and I'm happy to receive any questions.
Let me check. I think very clear because there are no questions.
Mm-hmm. So
Okay.
I apologize about before, about my connection was really bad. So apparently I think you couldn't really hear me very well at all, but I think it's okay now.
Okay, thank you. Okay. I don't know if Concha, Pedro is here. I give you a diploma about the tutorial.
Mm-hmm. Yeah, I'm not sure if they're here.
Well, on behalf of Mexican Artificial Intelligence Society, we thank Pedro, Concha, and Bojan for this interesting tutorial. We will be send the diploma to each one letter. Thank you very much for your time and for your knowledge.
Yeah. Thank you very much, Gustavo, and everyone involved for having us and for organizing this conference. And I hope you find the lectures useful and that some of you continue to learn more about this topic further on.
Thank you, Bojan.
Thank you
very much.
Bye.
Thank you for all attend to this tutorial.
Okay. Thank you. Bye-bye.
Thank you.